So today I'll be talking to you about open problems in mathematics. Okay? The purpose of the lecture will just be to acquaint you with some open problems, some simple sounding problems that are still unsolved in the field of mathematics. Okay? So there's four basic categories of problems that I'll talk about, four areas of math. The first area is number theory. All right? We'll discuss some open problems in number theory. This is an area of math that is sort of known for producing very simple sounding problems that turn out to be very, very difficult. Okay? So I'm going to try to keep this accessible to first years. Nothing too difficult, no Riemann hypothesis, no P versus NP. Okay? Just simple to understand questions that turn out to be very difficult to solve. Okay? So let's begin. Number theory. So I better tell you what this field is. Number theory is the study of whole numbers, okay, and their properties. So prime numbers, for example, are a very hot topic. This is what a prime number is, if you haven't heard the name. Prime number is a number that has no factors, or no divisors, other than 1 and itself. Okay? So here's an example of a prime number, a really stupid example. 2. Okay? 2 is a prime number. Nothing divides into 2 perfectly except 1 and 2. Okay? Another example would be 3. 4 is not going to be on our list because it's 2 times 2, but 5 is. 6 also isn't. It has factors 2 and 3. 7 is a prime number, and so on. The next one after 7 turns out to be 11, etc. Okay? Here's an open question about prime numbers. Does there exist a formula for them? Open question. Is there a formula for the prime numbers? Okay? And what I mean by formula is a function, f, which takes in, say, a natural number n. Okay, this is a natural number, and it spits out the nth prime number, Pn, nth prime. Okay? Mathematicians think the answer is no. Computer scientists think the answer is yes. Neither of them can solve the question. Mathematicians can't prove that a formula like this doesn't exist, and computer scientists can't find one. Okay? So a formula for the prime numbers, of course the formula has to be finite. It can't be some sort of infinite sum or some sort of infinite computation. It has to be an actual computable thing. You can program a computer then to find the first however many primes you want according to this formula. Okay? So there's our first open question. Let's put the board up. Okay, so what kind of progress has been made on this? Let's talk a little bit about that. Whoa, this is one of those boards that goes up. Progress. So a few simple things are known. So first of all, the formula, looks like I'm going to have to hold this down. Whoa, okay, that's too far down. Okay. All right. So the best case situation would be to actually find a formula for the nth prime number. Okay? A function which you plug in the number n, it spits out the nth prime. Something slightly weaker than that would be to find a function which maybe tells you whether the number you plugged in is prime, or it tells you if it isn't. Okay? So something which sort of characterizes the primes. We do have a result like this, and if you take number theory on this campus, Math C15, you're going to actually see a formula like this, which looks very simple, but the problem with it is it's useless. So I guess I better tell you what it is, and then we'll discuss why it's not a very useful formula. So Wilson's theorem. So this is what Wilson's theorem tells you. That n minus 1 factorial is equivalent to n minus 1 mod n if and only if n is prime. Okay? Let's define these symbols. N minus 1 factorial is the product of all the numbers up to n minus 1. So this is equal to 1 times 2 times 3 all the way up to times n minus 1. And what the mod does is it checks divisibility. Okay? So n minus 1 factorial is equivalent to n minus 1 mod n. What that tells you is that n minus 1 factorial, when you attempt to divide this number, whatever it'll be, by n, you get a remainder of n minus 1. Okay? Another way of saying that is, if you bring the 1 over, n minus 1 factorial plus 1 is divisible by n. Okay? It turns out that this is true whenever you plug in n being a prime, and it fails whenever you plug in n not a prime. So, for instance, 11 factorial, which is a pretty large number. Let's go with something smaller so that I actually know the answer. 7 factorial, okay? If you plug in, so 7 is a prime, so we got to plug in actually 7 minus 1. We got to do 6 factorial, okay? 7 minus 1 factorial is going to be equivalent to, according to the theorem, 7 minus 1 mod 7, okay? And you can test that. This is going to be 6 factorial, or 720. That's what it turns out to be equal to. And you can actually test that 720 is in fact equivalent to 6 mod 7, or that 7 divides 721, okay? And of course, if you sub in 6 in here into the formula and attempt to do this computation, you're not going to get 5 over here, okay? So this formula does characterize the primes. The reason why it's useless is because checking that a large number is prime requires you to compute a very large factorial, which is just as difficult. Okay, the factorial increases faster than even an exponential function. So this is useless for all practical purposes. Okay, sad face. Let me tell you about another useless result. Maybe I should bring that one down and write on this board over here. So, another useless result is Mills' theorem. And this was done considerably later than this. So this was from the 19th century, actually. Where's Mills' theorem? This is 19th century.
Excuse me.
Yep.
I think there is it's factorial on both sides, right? I mean,
Is it?
I think there's an exclamation mark on the right side as well.
Here?
Yeah.
I don't think that's the case. Because n minus 1 factorials would, no, there wouldn't be an exclamation mark here. No, I'm pretty sure of that. And look it up and let me know if I'm wrong about that, okay? If you have your phone with you. So that was from the 19th century. This result is from the 20th century, 1947 actually. So this is what Mills' theorem says. There exists a constant. It's called Mills' constant, A, in the real numbers, such that if you compute the quantity A to the 3 to the n for any natural number n, you get a number that's very close to a prime, okay? Such that that is very close to a prime for n in the natural numbers, okay? In the sense that if you take the floor of this number, so you take the number and round it down to the nearest integer, you get a prime for every n, okay? So close to a formula for the prime numbers, this thing generates only prime numbers if you sub in natural numbers. However, it misses a lot of them, okay? So a to the 3 to the n, as n gets large, this is going to increase very quickly, and you're going to end up skipping over a lot of primes and only getting a subset of them. Another problem is we don't know how to find the value of the constant a. Really, the only way we have is to guess the constant by actually setting this thing equal to some primes, which of course makes the formula useless for actually determining primes that come up later on, okay? So this is another useless result, and there are other things like this. I mean there's also something called Wright's sequence. Which tells you that there exists an alpha in the real numbers such that 2 to the alpha, 2 to the 2 to the alpha, 2 to the 2 to the 2 to the alpha, and so on, is a sequence composed entirely of prime numbers. But again, this theorem is pretty useless in practice. Okay, can't be used to find primes. So there was the open question. This is the progress that's being made so far. Not very encouraging. All right. What else can we ask about prime numbers? Let's wipe away this board. Okay, so there is no formula for them, or at least it appears that there isn't. Here's a very simple observation made in the 18th century that we still cannot prove. Okay? So another open problem, conjecture. Here's what it is. Every even number can be written as a sum of two primes. Okay? I guess I better put every even number greater than or equal to 4, because we want to rule out 2, which is too small. Okay? Can every even number be written as a sum of two primes? Well, let's choose an even number and test this thing out. So, anyone have an even number to suggest? Yes?
12.
12. Let's try writing 12 as a sum of two primes. Okay? There's the number. There's the two primes. Okay? We can also do something else here. We can do, can we do something else?
42. 242.
Yeah, no, we can't. No, we can't do anything else. I guess we can write 2 plus 5 plus 5, but that's not going to be 2. Yeah, no, see, 1 is not a prime number. Okay? So for 12, that's it. There's only one way to write this as a sum of two primes. For a number like 10, we can write 10 in two different ways. We can write it as 5 plus 5, or we can write it as 3 plus 7. Okay? So what this conjecture says is that every number has at least one representation like this. The larger the number you choose, the more likely it is that there'll be many such representations. Like if you choose 30, for instance, you can write 30 as 23 plus 7, or 19 plus 11, or 17 plus 13. I don't know, maybe there's something else. Okay? So you can play around with this and verify that this conjecture works. It's already been verified to work for all numbers up to something like 10 to the 18. By computer. But it's still unsolved. Nobody can prove that. And it seems so simple. Okay? So this was introduced, by the way, in 1742 by a guy named Goldbach. And now it's called Goldbach's conjecture. In a letter to another famous mathematician named Euler. Okay? Euler wrote back saying this is an almost certain theorem, but unfortunately I cannot prove it. Okay? Must have been a little embarrassing for Euler. Of course, not anymore. All right, so that's Goldbach's conjecture. What progress has been made on this? Let's bring down this one. I haven't used it yet. Let's hope it's not one of those that goes up again. No, it's good. So progress on Goldbach. It has been proved very recently that every number can be written as a sum of 3 primes. Every odd number, actually. Every odd number can be written as a sum of 3 primes. So this was called the weak Goldbach conjecture. Why? Because this result is stronger than this one, in the sense that if somebody can prove this, this result would follow quite quickly. Okay? However, if someone proves this, they can't conclude that. It's a one-directional implication. So this was called the weak Goldbach conjecture. also conjectured by Goldbach in the same letter as this was, of course, as a natural consequence. And it was proved only a few years ago, in 2013. Okay, using some sophisticated techniques. I better specify what kind of odd numbers we're talking about. Greater than or equal to 7? Yeah, I think it's 7. There we go. 5 can't be done. All right. So there we go. So there's some progress that's been made. What other progress? Well, by way of computer, we could test this out. There's also some theorems which talk about probability. Okay, so a probability result. Somebody proved in the 20th century, I think it was 1975, I don't know, you can check that yourselves, that the probability that a number chosen at random can be written as a sum of two primes is 100%. Of course, from that we can't conclude that every number can be written as a sum of two primes, because there are infinitely many numbers. So if the answer you get for the probability is 100%, that logically leaves open the possibility that infinitely many numbers cannot be written as a sum of two primes. Just like there are infinitely many numbers which are not perfect squares. And essentially 100% of numbers are not perfect squares, if you look at the density of them. However, there are also infinitely many numbers which are not perfect squares, they're perfect squares. Okay, so think about that yourself. So that's a probability result. 1975, that probability random natural number can be written, so much writing, I should have just spoken it, can be written as sum of two primes equals 100%, okay? One more result. Mathematicians have actually guessed roughly how many ways a number n can be written in this way. Okay, so a little bit of guesswork. For n in the natural numbers, there are approximately n over c times n over log squared n representations, where c is a constant which is close to a half. Okay? So if you plug in, say, 100 into this formula, you get 100 over, log here is the natural logarithm. Okay? So you compute the natural logarithm of 100, which is equal to, I don't know what, but you can do that. Square it, divide out the numbers, divide it by 2, which is what the constant is roughly equal to, and you can see that 100 can be represented by, roughly how many ways. Okay? So there's a little bit of guesswork, but it's not a stupid guess. This is actually a pretty good guess. Okay? Coming from the prime number theorem. All right, what else? So that's Goldbach's conjecture. Let's put this up. Let's bring down the other board. Here's another very simple question about primes which is still unsolved. The twin prime conjecture. So it was known since about 300 BC that there are infinitely many prime numbers. Euclid proved that. Euclid proved 2,300 years ago, 300 BC, that there are infinitely many primes. Okay? Which is kind of impressive for somebody in that day to do that. Okay? Here's what he didn't prove, but I'm sure he wondered about it, since it's known that the Greeks actually looked at this, but it's not known whether they actually formulated this conjecture at the time. It was formulated later in the 19th century as a special case of a more general result that was formulated, or a more general conjecture, rather. So here's what the conjecture is. Here's what was wondered about. Are there infinitely many twin primes? And twin primes are primes that differ by 2. So here's an example of a twin prime pair. 5 and 7. Another example, 17 and 19. Another example, 29 and 31. And so on. There are many of these pairs, when the numbers are small, they thin out pretty quickly as the numbers get large, but nobody knows whether there's infinitely many of them or not. Perhaps there is some final largest pair of twin primes, and then nothing else after that, okay? It's not known. Nobody can prove that there's a largest pair, nobody can prove that there are infinitely many, okay? So this is a special case of a more general conjecture made in the 19th century. That states that there are infinitely many primes, spaced a distance 2n apart for any natural number n. Okay? For all n in the natural number. So the twin prime conjecture is the n equals 2 case. Okay? And then this is a more general conjecture. Okay? So, of course, the conjecture hasn't been answered for any special cases, but there has been a little bit of progress made. So what is the progress that's been made here? I'll write on the bottom board, even though that's illegal. Professors almost never write on the bottom board because then all the boards will cover this up, but we'll move over there. So progress. What has been proved about this? Very recent progress. Again, in 2013, somebody proved that this conjecture is true for certain values of n, but he didn't say for which ones. Okay? So the guy's name was Yitang Zhang, spelled like that, in 2013. He proved that there exists a number n, okay, which is less than 35 million, for which this conjecture holds. Okay? There exists an n less than or equal to 35 million, okay, for which that conjecture above, okay, turns out to be true. But he didn't say what that value of n is, okay? So this caused a pretty big buzz because before 2013, people thought that this result was somehow out of reach of present-day mathematics. New math would have to be developed in order to answer this question, these questions. Okay, so this guy proved everyone wrong. In about a year's time, his method was used and improved, and somebody came up with a simpler way, actually, to prove the same result as he did. Two guys, Terence Tao. Okay, I spelled Tao with an actual Tao. Terence Tao and James Maynard, a British guy. I think he's only like 30 years old. Proved a stronger result, that n only has to be less than 264. So a major improvement. Now 264 is 2n. There we go. You guys do the division. 132. Okay, so n less than or equal to 132. Okay? A little bit more progress. This is 2014, by the way. In a couple years' time, or maybe in a year's time or so, assuming another unproven conjecture, this guy over here reduced the bound to 3. Okay? Assuming another open problem, which mathematicians think is true, n has been reduced to 3. So, whoa, I just dropped the chalk. So, what this result tells you is that there are infinitely many primes that are either spaced a distance 2 apart, or a distance 4 apart, or a distance 6 apart. What we think is that there are infinitely many of each type, but nobody can prove that. This is the best result we have, and it's actually pretty good. A lot of progress has been made, because in 2012, nobody even suspected that this was possible to be proved. And now all of a sudden, a year or two later, we have this result. Okay? So some progress, but not enough. We still think there are better techniques available that hopefully will get invented at some point that will allow us to actually solve this problem for all n. Okay? Just something new that no one's ever thought of, a new approach. All right, so that's the twin prime conjecture. Are you guys getting tired of primes yet? Maybe we should move on to something else.
Make it entertaining.
Sorry?
I said you make it entertaining.
Okay, cool. So maybe one more question about primes, and then we'll move on to something else. What form do primes come in? So another open problem. This one is actually kind of relevant because a guy on this campus did some work on it. Open problem. What form do primes come in? Okay? So suppose we choose a function, okay? Like n squared plus 1, a polynomial in n. Does that polynomial hit infinitely many primes? That's an open problem. Does n squared plus 1, when n is a natural number, hit or equal or is that prime infinitely many times? Infinitely many times. Okay? So let's take a look at some examples. If we substitute n equals 1, out pops a prime. 1 squared plus 1 is 2. That's prime. 2 squared plus 1 is 5. Also prime. 3 squared plus 1 is 10. That's not prime. But 4 squared plus 1 is prime again, because it's 17. Okay? And we can keep going. 6 squared plus 1 is 37, which is also prime, etc. Okay? So this polynomial in particular, n squared plus 1, it looks as if it hits a lot of primes. Every now and then there's a prime. Okay? But we cannot prove that it hits infinitely many primes. In fact, more is true. We can't prove that any quadratic or higher degree polynomial hits infinitely many primes, although we do think that it's true. Okay? So it's a general open question to find whether higher degree things hit infinitely many open primes, or perhaps we could change the coefficients here, something maybe like 3n squared plus 2n plus 1. Is that prime infinitely many times? Of course, you choose something which doesn't factor straight away. You don't want to be stupid, right? So does something like that hit infinitely many primes? Okay, it's unknown for any expression of degree 2 or higher. Okay? So maybe I should wipe that away. Does any quadratic or higher degree in one variable hit infinitely many primes? Okay? Open question for any expression. All right? The question has been answered only in the linear case, only in the case where you have something that looks like an plus b. Okay? This one has been solved, okay, by Dirichlet, 19th century. Of course, a and b here can be any natural numbers, and we do not want them to share a common factor for obvious reasons. No common factor for a and b. Okay? So, in particular, you set 2 and 1, something silly like that, you get that there are infinitely many odd primes. Well, no shit. But you can set a and b to be something more interesting, like 3 and 1. Then you get that there are infinitely many primes which are 1 more than a divisor of 3. Okay, and you can set these things to be anything you want. Okay, so this problem was solved. However, if you tweak the exponent, put it up to 2, all of a sudden the question is not answered. Okay, the question has been answered for an exponent of 2, but only if we allow 2 different variables. Here we only had a 1 variable, n. Okay, if we allow 2 variables, like if we consider n squared plus m squared, something like that, where n and m are both free, then the problem also has been answered. Actually, it's not that difficult to answer it. Perhaps you'll see it in C15 if you take C15. It's called Fermat's theorem. Although it wasn't Fermat who proved it, he just conjectured stuff and then wrote it in the margins of his books. He didn't actually prove much himself, or maybe he did, but he didn't let the world know. So Fermat's result a squared, that's right, n squared plus m squared hits infinitely many primes. Okay? And the key here is that n and m are both natural numbers, but they're independent. So actually, a lot of numbers can be written like this, as the sum of 2 squares, just because you have the 2 variables to choose from. So the result that he proved is actually slightly stronger than this. He actually said which primes can be written in this form, and which primes cannot. If p is equivalent to 1 mod 4, then we're good. If p is not equivalent to 1 mod 4, okay, so the only other possibility is it's 3 mod 4, then no. Okay? So only if the prime has a 1 remainder left upon division by 4, but not in the other case. So about half the odd primes can be written like this, and half the odd primes cannot. Let's see an example. 5. That leaves remainder 1 upon division by 4, so we should be able to write it as a sum of 2 squares, and we can. 5 is equal to 1 squared plus 1 for a minute there. Okay, there we go. So that's Fermat's result. He was right. What else can be done? We can modify the exponents slightly on this. So if you are allowed to use 2 variables, you can actually tweak the exponent to make it a higher degree and still get a proof that there are infinitely many primes that can be written like that. So this is a result that was actually proved for the first time by somebody on this campus. Okay? A guy named John Friedlander. Proved in 1997, okay, so quite a few years ago, with another dude, with another mathematician, I'm going to write dude, with another dude, that n squared plus m to the 4th hits infinitely many primes. Infinitely many primes. Okay? So that is actually a very interesting result because there are significantly fewer 4th primes than squares. Okay? This hits infinitely many primes, but again, we don't know which ones. Okay? But we know that it does generate infinitely many primes. Okay? So I think this was the first time that a result like this was obtained, where you had 2 variables and the exponents were higher than 2. Okay? So that's what he proved. The paper itself is 96 pages long, okay, and completely incomprehensible to any normal human being. I looked at it myself and I couldn't get past the introduction. Okay, but it is up online on his website, so you can have a look at that. So this is the result that he's sort of known for, okay? And he is on this campus. He still comes here. He's 76 years old or 77, something like that. And he still comes here and he even teaches a class sometimes. He might teach number theory, okay? All right, so that's sort of interesting. Little connection to this campus. This conjecture, by the way, the special case of n squared equals n squared plus 1, that's called Landau's conjecture. Okay? Of course, we can then look at other functions and see if they get infinitely many primes. Functions which aren't polynomial, but are exponential. Okay? So here's another open question. Does 2 to the n minus 1 hit infinitely many primes. So these are called Mersenne primes. And they're going to be relevant to what we're going to do in a minute. Mersenne primes, that's supposed to be spelled with a capital letter. There we go. So here's an example of a Mersenne prime, 31. It's equal to 2 to the 5 minus 1. Okay? 32 is 2 to the 5 minus 1 is 31. There's a Mersenne prime. And of course there are others, like 7 is a smaller example, 2 to the 3 minus 1. And then we could come up with higher and higher examples. Actually, the largest primes that are known now are the Mersenne primes, because it turns out we have a bit of a shortcut available for checking whether numbers in this form are prime, and we can just program a computer to find larger and larger ones. So there are 50 of these known. Whoa, the chalk just broke midway. 50 known. Most were found by computer. Okay. The largest one which was not found by computer is 2 to the 127, not 127. Yeah, 127. No, check me on that. Okay? 2 to the something over 100 minus 1. This is the largest one that was actually verified by hand. Okay? The largest one that was verified by computer is 2 to the 77 million. Okay? Minus 1. So this is a number with something like 23 million digits. Okay? And of course it was found by computer. Okay, so that's the largest prime known, and it's the largest Mersenne prime that's known. But there are only 50 of them known so far. And of course it's conjectured that there's infinitely many that can be written in this form. But again, no one can prove this. It seems to be an even harder question than those ones up there, because those ones were concerning functions that were quadratic or quartic degree or something. This is an exponential. There are significantly fewer terms there are significantly more gaps along the way, okay, when we consider those numbers there. So let's leave primes. We've been spending too much time on primes, haven't we? Let's talk about something else. Let's talk about something called perfect numbers. Let me write over here. So another number theory question. Perfect numbers. Okay, so what is a perfect number? A number whose proper factors add up to itself. Whose proper factors add up to itself. Okay? So here's an example. So what does proper mean, first of all? Not including the number itself. So here's an example. 6 is a perfect number, because 6 is equal to 1 plus 2 plus 3. These are all divisors of 6. The sum of all the divisors of 6 adds up back to 6. Here's another example. 28. What are the divisors of 28?
2.
Yeah, 2. Well, 1 is always there. Plus 2 plus, what else? Does 4 go into it? Yeah.
7.
That's right. 14. And that's it. 28 itself doesn't count. Okay? And if you add this up, you get 1 plus 2 is 3, plus 4 is 7, plus 7 is 14, plus 14 is 28. Good. Okay? It turns out that these are actually pretty rare. These are rare. The next example after 28 is 496. Okay? Okay? Is next. And then the next example after 496 is 8,128. So they get spaced out by larger and larger intervals. Okay? And nobody knows whether there are infinitely many of these or whether there are odd perfect numbers. So far, the only perfect numbers we found are even. Okay? These four were actually known to the Greeks. 6, 28, 496, and 8128. Known to the Greeks. We have no idea how they knew them. Did they just choose numbers and try to experiment and see if the factors add up? All the way up to 10,000 almost. I don't know. But those four were known to the Greeks, so 300 BC. okay, Euclid's time. And possibly they also wondered about having a formula for these, or being able to determine what the next one is, or being able to sort of characterize what form these numbers take, okay? And also whether there are perhaps odd perfect numbers, okay? So what did they prove? So Euclid, again, proved that a number that looks like this, 2 to the n minus 1 times 2 to the n minus 1, where n is a natural, is perfect. But only when this number over here is a Mersenne prime. Okay? There we go. So Euclid proved that. Euler actually reversed the implication and showed that every even perfect number has to take on this form. And that wasn't until the 18th century. So there was like a 2,000-year gap there. Okay? Euler proved reverse implication. Okay? And this was in 18th century. Okay? So we now know what the even perfects look like. They have to take this form. So we know that there are at least 50 of them, because there are at least 50 Mersenne primes. The conjecture is that there are infinitely many even perfects, and of course that is unsolved, and is equivalent to the Mersenne prime. Let me switch boards here. Get the eraser. Oh, this is the bad one. Okay, so open problems. There's 2 of them here. Are there infinitely many perfects, even perfects? Infinitely many even goes here. All right, that's one open problem. It's equivalent to the Mersenne question. A second open problem is, are there any odd perfects? So far, the only perfect numbers we know of are even, okay? The thought here is that no, there are no odd perfect numbers, but nobody can prove that, okay? The Greeks presumably wondered about this problem as well, because they did wonder about the formula question, so they probably did wonder whether the formula generates all even perfects, and if it does, then what about the odd perfects? So presumably the Greeks did wonder about this, and that would make this the oldest unsolved math problem, 2,300 years old, okay? And it's still unsolved to this day. What we know is that if there is an odd perfect, so let's look at the progress over here that's been made since then. Progress, somebody proved that if odd perfect exists, then it's greater than or equal to, that doesn't matter actually, 10 to the 1500, okay? There's a result. So it has to be huge, absolutely huge, okay? What else do we know? There's a bunch of little results, like n cannot be divisible by 105 if it turns out that it's an odd perfect, and so on. And there are many results which sort of make it very, very clear that if an odd perfect number does exist, it's super, super elusive and super large, okay? So chances are there isn't one, but we can't prove that, okay? So there's another open problem. All right, let's move away from this kind of stuff and talk about something not related to number theory. I don't know, maybe one more number theory problem. I sort of can't mention Fermat's last theorem. I have to mention that. Let's wipe this away. Do you guys want a break by any chance? 2 minutes? Okay, good. Cool. Okay. For the review seminars, the classes always ask for a break. All right. So I'm going to call this Euler's conjecture. Okay. There we go. So like a generalization of Fermat's last theorem, or Fermat's conjecture. So maybe I should first introduce Fermat's last theorem, in case you haven't heard of it. So Fermat's last theorem says the following, that there are no solutions to the following equation: a to the n plus b to the n equals c to the n. And of course, these are whole number solutions, integer solutions, okay? A, b, and c are integers, okay? These are all integers or natural numbers. Turns out the question for odd ones is equivalent. N is a natural number which is greater than or equal to 3. Okay? So of course, if n is 2, then we get a Pythagorean triple. So we do know that there are infinitely many of these. We know exactly what they look like. That problem has been solved. Then people started wondering what happens when we increase the size of the exponent. And the conjecture here is that this really should be called Fermat's last conjecture, because he never gave a proof, although he said he had one, but he was a liar. He did not have one. Okay, Fermat's last conjecture is that there are no integer solutions to this for any of these exponents greater than or equal to 3. Okay? Of course, if you do allow 3 terms to be added up, then there are solutions sometimes. Okay, so maybe a little more about this problem. This was unsolved since the 17th century. Okay, so Fermat made this famous conjecture in the 17th century. A lot of people have tried this problem. Nobody could do it, especially in the 18th and 19th century. A lot of people tried the problem. Fermat himself proved the n equals 4 case. For n equals 4, okay? Using a method called infinite descent. Descent. Okay, there we go. All right, so Fermat proved for n equals 4. Euler proved for n equals 3. Okay, so this is the 18th century now. And then another mathematician named Sophie Germain I'm not sure how you spell that, I think like that, proved that, or rather reduced the question to all prime exponents n. So she basically solved the question for n equals 6, n equals 8, and so on. And basically said that the problem would be solved if we can prove this for all prime n. Okay? Let me write, reduce the problem. Question to prime n. Okay? But the general case was still unresolved all the way up until 1995, and a guy named Andrew Wiles finally proved this in 1995. And it took him 7 years to do. 100-page proof. Okay? And apparently he didn't really do anything else during those 7 years. So he just locked himself in his attic and was working on this problem for 7 years straight. And his wife was, I guess, making him food and delivering it to him, and he was just sitting up there all the time. That's at least what the story goes. So, turned out to be a very hard problem. He was awarded several awards, actually, for solving this. But the methods he used were very, very advanced, far too advanced for Fermat. He claimed that he had a proof of this that was quite simple. He wrote that, of course, in the margin of his book, and then he followed up with, unfortunately, I can't say what I did because the margin is too narrow for me to write down the proof in there. Okay, so he sort of left the open question that way to the world. Okay, so there's Fermat's last conjecture. Now, we didn't talk about Euler's conjecture at all, so I guess we better put that in here. So Euler tried to generalize the problem. He thought, well, there are no solutions here when you add up 2 numbers, 2 powers of 3, let's say. 2 powers of 3 can never add up to a 3rd power of 3, but maybe you need more powers. Like maybe 3 objects here, 3 powers of 3, will add up to a 3rd power of 3. And it turns out that that's true. You can find 3 powers of 3 which add up, and I think the example is 1 cubed plus 6 cubed plus 8 cubed. I think that that's 9 cubed. Anyone here with a calculator can check that. But anyway, correct me if I'm wrong. This is true. Okay, so we can have 3 powers of 3 adding up to a power of 3. Euler also noticed that you can't really have 4 powers of 3, or sorry, 3 powers of 4 adding up to another power of 4. At least he couldn't find such an example. So he conjectured that maybe you need 4 powers of 4 in order to add up to a power of 4. And then 5 powers of 5 in order to add up to a power of 5, and so on. Okay, so that's Euler's conjecture. It made in the 18th century. Okay, so what is the conjecture? You need n powers of n to add to another power of n. Okay? And nothing smaller will do. Like you're never going to find 7 powers of 8 which add up to another power of 8. So he thought that maybe by generalizing this problem, he could, perhaps the general problem would be easier to solve now, and then he could sort of get Fermat's last theorem as a special case. But that ended up not. He couldn't prove his conjecture, and that's because it was false. Board down. Okay, so this actually wasn't resolved until the 1960s. A couple people, by way of computer, proved Euler wrong. Okay, so in the 1960s, example was found of 4 powers of 5 adding up to another power of 5. Okay? 4 powers of 5 adding to power of 5. The example was big. Okay, there were 3-digit numbers. Okay, so a 3-digit number raised to the power of 5 plus another 3-digit number raised to the power of 5 plus dot dot dot. 2 things are filled in here, and that apparently added up to another 3-digit number to the power of 5. So there was no chance of Euler ever finding this himself because a 3-digit number raised to the power of 5 has at least 15 digits. It could have up to 20. Okay, so there we go. So when Euler was wrong, he sometimes was wrong, but not in any obvious way. Okay, so this conjecture was a very good guess at the time. It turned out not to be correct. So this example was found, and since the 1960s, 2 more such examples were found. It was also found in 1986, so right about the time that Andrew Wiles started working on his Fermat's last theorem, that you can have 3 powers of 4 adding to another power of 4. Another power of 4. Okay? And this was done by a guy named Noam Elkies. Okay? Also by way of computer. And then he actually did some math after that. So he didn't just use a computer and call it a day. He actually proved that there are infinitely many such solutions. Okay? Now, besides that, not that much work has been done, or not that much progress has been done about this, about solving this problem of, well, we know that we don't need n powers of n to add up to another power of n, but perhaps there's something, at least you can say, about this. Perhaps sometimes you can have n minus 1 powers of n adding up to a power of n for certain n's, okay? Or perhaps there's some sort of formula or something you can say about how many powers of n you need in order to make another power of n. That's still an open problem. So that's still open when it comes to Euler's conjecture. Is there some sort of rule? Okay? What else do we know about this? We know that there are 6, I think, powers of 7 which add up to another power of 7, and 7 powers of 8 which add up to another power of 8. That was found a bit later. Okay? But besides that, the conjecture is open. For the n equals 6 case, I don't believe we found anything yet. Okay? All right, so that's about it for number theory. I don't want to talk about number theory the whole time. We skipped over a couple things. Because I actually prepared for this, believe it or not. I wasn't going to do that. I was just going to come in and talk like I always do for the review seminars. But then people from AMACSS said, we we planned this, we booked the room, we're gonna advertise it and so on. You better not make a fool of yourself. More importantly, you better not smear the AMACSS image. So you better prepare for this. So I prepared a few things, but I prepared too much. All right. So let's move away from number theory. Let's talk about analysis. Okay? Something quite different. Analysis. So, what analysis is sort of the study of functions. So quite different than the number theory we were talking about, which concerns whole numbers. Okay. Here's a question that was posed from analysis in the 17th century. So 1644, I think it was. A guy named Mengoli asked the following question: what is the sum of the reciprocals of all the perfect squares? So what is 1 squared plus 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... equal to? Can we find the exact value of that infinite sum? Okay? And this remained an open problem for 80 years. 90 years, actually, closer to 90 years. Okay? And then it was finally solved by Euler. And Euler found that the sum is actually equal to a most unexpected value. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. That infinite sum actually adds up to pi squared divided by 6. So same pi that appears in circles. Okay, so maybe now would be a good time for a break.